Today we are solving swim in rising water problem. We are given an n cross n integer matrix grid. N cross n means this is a square matrix where each value represents the elevation at that point. We have to return the least time it takes to get to the bottom right square from the top left square. We also can swim infinite distance in zero time. What does it really mean? It means, for example, in a path like this, we can swim along this path in zero time. So wouldn't the time required to get to the bottom right square from the top left square be zero? Unfortunately, the problem statement is not that simple. There is a constraint for us to begin swimming, which is mentioned over here. I don't know why Leetcode made it really convoluted. I'll try to paraphrase this constraint. This constraint basically says, regardless of whichever path we take, before we can start swimming, we need to wait certain amount of time. So what exactly would that certain amount of time be? It depends on the path we take. For example, if we take this path from the top left to the bottom right cell, amount of time we need to wait before we can start swimming will be the maximum elevation in this path, which is 5. So we need to wait for t equal to 5. Let's look at a different path. In this path, we need to wait for t equal to 4 before we could start swimming along this path. So basically, the problem statement is asking us to find a path from top left cell to the bottom right cell that has the least maximum elevation. So it has the least maximum elevation. To solve this problem, how about we explore all the possible paths, and for each path, we note down the maximum elevation in that path, and we return the minimum of all the maximum elevations in each and every path. This algorithm will definitely give us the right answer, but the runtime for this algorithm is exponential. Can we do better than this? As we know, what's driving the wait time before we could swim along a path is the maximum elevation in that path. So how about we avoid cells that have the maximum elevation? For example, 5. How about we avoid all the paths that go through 5? This will help us prune all those paths that go through 5 and should bring down the runtime complexity. How about we do the same for all the paths that go through 4? This is a really good way of pruning all the paths that have higher elevation. In other words, what we are saying is, from any cell, we pick an adjacent cell to swim to that has the least elevation. For example, from the top left cell here, there are two cells that we can swim to, cell 1 and 2. So we pick 1 because that has the least elevation among all the potential paths. Then we add its neighbors to the queue. In this case, 4 and 5. So there are 3 cells in the queue now, 2, 4, and 5. We always pick the cell that has the least elevation, in this case 2. We add its neighbor to the queue, which is 3. Out of 3, 4, and 5, 3 has the least elevation. We pick 3 and add 2 to the queue. We repeat the same, 2 has the least elevation. We add 3 to the queue. And out of 3, 4, and 5, 3 has the least elevation, and that happens to be our destination cell as well, so we stop the algorithm here. And the path we took to get to the bottom right cell is this. Every time we pop a cell from the priority queue, it's because we are going to swim to that cell. That cell will be part of our final path, which means we should take its elevation into account in finding the least time to get to the bottom right cell. So every time we pop a cell from priority queue, we save its elevation and we return the maximum elevation. That's our final algorithm. So the runtime complexity of this algorithm is big O of n square log n square. Because in total there are n cross n cells, and we'll be pushing, in the worst case, all those cells into the priority queue. So we can simplify this further of n square. We can bring the 2 over here, 2 log n. We know that 2 times log n, when we generalize it, it is same as of n square log n. That's our runtime complexity. And the space complexity is O of n square because we need to mark all the visited cells. Let's write the code for this algorithm. Let's call n as the dimension of the grid. Since we are starting with the top left cell, let's add top left cell to the priority queue. Elevation of top left cell is grid of 0, 0, and the row index is 0, column index is 0. And we mark this cell as visited. Dot add 0, 0. While the priority queue is not empty, we know that priority queue always picks the cell that has the least elevation. So let's pop the cell from priority queue. Heap queue, heap pop from priority queue. We get the elevation, row number, and the column number from it. We check if this is a bottom right cell. If row equal to n minus 1 and column equal to n minus 1, that means we have reached our destination. We have to return the maximum elevation along this path. So let's call that as max elevation and initialize that to 0. So we return that. Before returning that, we need to update the max elevation if the current elevation is greater than the max elevation. If this is not the bottom right cell, we need to add the unvisited neighbors of this cell into the priority queue. So let's explore these neighbors. For new row and new column number in all the possible neighbors, which are row -1 and same column, which is the top cell, and row +1 column is the bottom cell. This is the left cell, and this is the right cell. If the neighbor is already seen in scene, we don't add this to the priority queue. If it's an unvisited neighbor, then we can add this to the priority queue. Heap queue, heap push to the priority queue, and the elevation of it is grid, new row, and new column. And the row number is NR, and NC is the column number. In the next round, we again pick the cell with the least elevation and keep updating the maximum elevation that we found so far. So this will ensure we always pick a neighbor that potentially has the least elevation out of all the possible options. So finally, we return the maximum elevation we have found. Oh, one thing I forgot to do here is I need to ensure this neighboring cell is not out of boundary. So if new row is less than 0 or new column is less than 0 or new row is greater than or equal to the number of rows or new column is greater than or equal to number of columns, in this case we skip this cell. I also need to add the unvisited neighbor to the list of neighbors visited. So let's add that. Scene.add nr and c. As you can see, this solution works. If you found this video to be helpful, please support by liking the video and subscribing to the channel. I will see you in the next video. Thank you.